Now that we've talked about kind of the two ways that we end up slicing things up, either geometric cross sections or discs slash washers, now we're going to talk about how that might get a little more complicated, specifically the discs and washers method. So before we get to that, I want to have us look at a general volume summary. So how do we find volumes of rotation? So first you have to understand, or this will work for anything actually, understand the structure and the geometry. So try and sketch it or visualize it in your head. This is something that if you struggle with spatial reasoning, it's something you'll need to practice. If it comes naturally, great, lucky for you. But it is something you'll have to kind of sketch out and imagine what each of these situations will look like. Next, determine whether to slice perpendicular to the x-axis or y-axis. So I believe in all the examples I gave you, we did have a mix where some were sliced, perpendicular to the y-axis. Some were sliced perpendicular to the x-axis. And the way you do that is just by imagining, again, if you understand the structure and geometry, imagine what it's going to look like and then say, okay, which of these slices give me the same kind of shape, either all discs or all squares or all triangles, etc., etc. And this will give you either dx or dy respectively. So if you slice perpendicular to the x-axis, you're making your slices dx thickness. If you slice perpendicular to the y-axis, you're making them dy thickness. Then determine the shape slash area of the cross section. So for example, pi r squared, base times height, etc. So whatever the equation is, figure out what that is going to be. Write the integral expression of the area times the thickness. And that thickness, again, will give you your dx or dy. Substitute any variables that aren't, substitute any variables as necessary. So if you had pi r squared, figure out what r is, substitute it in. And then lastly, integrate and solve. So this is the general strategy. This is when I approach a problem, what I do, I think about what does this look like, which way should I slice it, and then based on that slicing, what's the cross section, I write it down, again, not worrying about the variables from the problem yet. Then I substitute in the variables, then I solve it. So now let's look at an example where things get a little more complicated. Let R be the region enclosed by the line y equals 1, x equals 4, and the curve y equals x to the 1/2 plus 1. The solid is generated by rotating R about the line y equals 1. So first thing we got to do is imagine what this looks like. Well, it's going to look something like this when I rotate it. So notice this isn't rotating around the x-axis anymore. Now it's rotating around this line y equals 1. But that's okay. We can still, from that sketch and kind of thinking about it, we know that we're going to want to slice it perpendicular to the x-axis. So we're going to have slices of dx. If we're rotating it in a circle, we know that our area is going to be pi r squared. And we know that our thickness, again, we said is dx. So my integral is dx times pi r squared. Now, if I know that it's dx, that means I need to look at my x values for what my bounds are. And those bounds will go from 0 up to 4, again, from the problem here. X equals 4 and y equals 1 matches or intersects with y equals square root of x plus 1 at 1. So that's why or at 0. So we go from 0 to 4. That's pretty easy to see from the diagram as well. But the problem, again, can't have this r squared, so we've got to figure out what is r. Well, r is this distance right here. In other words, it's a y value minus 1. So r equals y minus 1. So I'm going to have the integral from 0 to 4 of pi y minus 1 squared dx. Again, it's dx, so this y isn't going to work, but we know that y equals square root of x plus 1. So the integral 0 to 4 of pi times square root of x plus 1 minus 1 squared. And nice thing here is that ends up working out as the integral from 0 to 4 of pi times x dx, and then this is something that you can continue integrating yourself. But again, for over and over, just to repeat this to get this clear and kind of in your head, find the area, find the thickness, and just write those down, and then just work substitutions until you get something that's integratable, meaning that it only has the variables that you care about. Here's a second example where we have let R be the region enclosed by the line y equals 4 and the y-axis and the curve y equals 1/2 x cubed. What is the volume of the solid when R is rotated about the line y equals 1? Y equals -1. So this is rotating now around this y equals -1 line. So we're going to get something that looks like this down below. It's a little sloppy because it's a little hard to draw, but you can imagine this kind of swings around. And then on the back side, it's also going to swing out and around. This kind of swings around to create a hole there. And then as we go up, we've got, other holes like that. And then finally at the top, we've just got this guy like that. So it's kind of a cylinder with a funnel cut out of the center, right? You can kind of hopefully imagine that, a cylinder with a funnel cut out of the center. And so let's think about, if it's a cylinder with a hole cut out of the center, we know in this case that we want our integral to be with respect to dx. And that's because looking at it, once I've sketched those lines on, it's really apparent that we want to slice perpendicular to the x-axis. And that means we want to take pi of the outer shape squared minus pi of the inner radius squared. So outer minus inner. What's the outer radius? The outer radius is actually pretty nice because it's a cylinder. It's y equals 4 minus y equals -1. So it is 4 minus -1, or 5. And that makes sense because we see it's constant. What's the inner radius? That one's a little more complicated. It's this distance here, which is y minus -1, which is 1/2 x cubed plus 1, because 1/2 x cubed minus -1. If we're integrating with respect to dx, we know that we want to go from 0 all the way to, was this 2 labeled on here? Yeah, all the way up to 2. So 0 to 2 of pi 5 squared minus pi times 1/2 x cubed plus 1 squared dx. And I'll help you work through this one a little bit because it is might be a little unclear at first how this works out. We're going to break it into two integrals first, 0 to 2 pi times 25 dx minus the integral minus pi times the integral, and I'm going to square that. So it's done, 1/4 x to the 6th plus x cubed plus 1 dx. And now hopefully it's a little easier to see what's going on here. This first bit will just be 25 pi x from 0 to 2, and then the second part is a polynomial that you should be comfortable with integrating. If you need help on it, let me know. But you can see how you'd continue working this through to get your final answer.